7.1 deals with exploring exponential models. Y equals a times b to the x might be what you're most familiar with dealing with an exponential model. Now, the easiest way to know that this is an exponential function is that my variable x is actually what's in the exponent. Now, we've dealt with functions that have exponents before, like a quadratic that has y equals like x to the second power, cubic functions where we have x to a cube, x to the third power. This differs and is an exponential model because that x itself is what the exponent is. Formally, an exponential function is a function with the general form y equals a times b to the x power. A cannot be 0, b has to be greater than 0 and not equal to 1. Base b is a constant, or we call b our base here, and that's always going to be a constant number. The two different types of exponential models you could have are exponential growth and exponential decay. Exponential growth is when a is greater than 0 and your b value, or your base, is greater than 1. And when you graph it, it would look something like this. Notice that I'm kind of increasing at an increasing rate here, which is where that curve comes in. Exponential decay, on the other hand, is when a is greater than 0 and b is between 0 and 1. So my base here is not negative, it's just a value between 0 and 1. And when I model it, my graph would kind of look like this. In both cases, that a value is your y-intercept. So to start here, just kind of simply identify each function as exponential growth or decay and state the y-intercept. In this first part, we have y equals 12 times 0.95 to the x power. 12 would be my y-intercept. That b value, 0.95, is between 0 and 1, so that's going to represent decay. In part b, 0.25 would be my y-intercept. That 2 is greater than 1, so this is going to represent exponential growth. Now, where exponential models can really become important is when we're modeling exponential growth or decay in a real-world situation. The most common examples for modeling exponential growth or decay could be growth in terms of if you're putting money into a savings account that's earning interest. In terms of exponential decay, you could be looking at an endangered species and like predicting when that species would actually be extinct. If you take medicine, how quickly that medicine leaves your body. Or like distributing medicine or like a vaccine to a disease and seeing how exponentially that disease, like that's prevalence would decay over time or decrease over time. The function that we use to model that is a of t equals a times 1 plus r to the t power. Now I know these are just a bunch of letters right now, so here we're going to break down what each of these represent. T represents your time period. So when we're modeling growth or decay, how long are we observing that growth or decay for? That A represents your initial or starting amount. R represents your rate of growth or decay. Notice here that this isn't necessarily our base. So if we have growth, we're going to be adding an R value. If we have decay, we have a negative number, we're going to subtract that. And finally, A of t represents the amount after t time periods. So for our first example, you invest $1,000 into a savings account at the end of your 6th grade year. The account pays 5% annual interest, and you want to figure out how much money would be in that account after 6 years. So I'm going to use this function, and I'm going to plug in the information that I have, and then just let my calculator spit out an answer. You invest $1,000. That's going to be your starting or initial amount. So for A, I'm going to plug in 1,000. Next, the account is paying you 5% annual interest. You're earning interest, so I know that this is going to be a growth function. So I'm going to be adding 5% to 1. 5% represented as a decimal is 0.05. So I'm going to add 0.05. Again, if I was losing money, I would be subtracting this here. But since I'm earning money, I'm adding 0.05 to this 1. Next, I want to know how much would be in my account after 6 years. So I'm going to plug in 6 for my t. Now from here, I plug this into my calculator, and it's going to spit out $1,340.10. So I can estimate that if I'm earning 5% interest every year, I would have around $1,300 after 6 years in that account. Now this example is pretty straightforward. We're going to mostly deal with examples like these. To end this video, let's look at a real-world example where the numbers are real here to kind of see where we could also model exponential growth or decay. So, Polio is an infectious viral disease that attacks tissue at and around the spinal cord, causing severe permanent paralysis. This disease was super serious. Thankfully, though, there was a vaccine that came out, and it's pretty much gone from the world today. We all have gotten our polio shot. It's one of the required vaccines that you get before coming to school, so we're all good here. Nothing to worry about. The vaccine for polio was developed in 1955. The table here, The table here shows the number of U.S. citizens with polio in 1954 versus 1955. So the year before the vaccine came out versus the year that the vaccine was available. Using this data, we want to estimate how many polio cases there would be in 1995. Now, I know you could just Google this. We're going to pretend that we're back in time and we're scientists in 1955 trying to predict to see how successful this vaccine would be given the data that we have. Now, again, we're going to use this model here, this function, but we're going to kind of have to work to find some of our values here. They're not as straightforward or given to us like that last one. To find our rate for an exponential model, here's how I would do it. I take my y2 value minus my y1 value and divide it by my y1 value. So here I'm going to take 28,985 minus 38,476 and take that over that 38,000 number. When I do that, I get negative 0.25, just rounding up here. Negative 0.25 makes sense because, again, I distributed a vaccine, so the number of cases are going to go down. I plug that in for R, so my base value here is 0.75. So notice here this represents decay. I have a number between 0 and 1. I'm good to go to move on. Now I'm starting my data in 1954, so I'm going to use that 38,000 number as my initial amount here. So again, this is initial in the sense that this is where I'm starting my data at. So I'm going to plug in 38,476 for A. Finally, to figure out T, or my time period, I'm starting in 1954. I'm making a prediction for 1995. So that's a time difference of 41 years. So I'm going to plug in 41 for my T value. When I plug all this in, so I'm going to do 38,476 times 0.75 to the 41st power. When I plug that in, rounding up to the nearest whole numbers, I'm talking about just human beings here, so I can't have a decimal, I would get around 3. So that kind of would tell me as a scientist back in 1955, okay, if my data continues along this trend, this disease is pretty much going to be completely gone by 1995. So that would be helpful information to know.